April 12, 1910. Locomotive 460 hits 90 miles per hour. A speed engineer swore would tear it apart within weeks. So how did this death trap become unbreakable? Through the coal smoke and steam, the PRR E6s Atlantic proved every calculation wrong. The 442 wheel arrangement generated power levels that Baldwin's senior engineers had declared mechanically suicidal. Driving wheels measuring 80 inches in diameter spinning at speeds that should have torn apart frame rails designed for locomotives half as powerful. Yet number 460 maintained smooth operation that defied everything established. Steam engineering predicted about structural limits. In locomotive works across America, high-speed passenger service maxed out at 70 miles per hour with engines built conservatively to prevent catastrophic mechanical failure. Sustained running above 80 miles per hour meant frame cracking, driving box failures, boiler explosions from pressure surges that conventional safety systems couldn't manage. If you want to see more videos about old trains, make sure to subscribe so you never miss another video. Most manufacturers accepted these limitations as fundamental laws of steam power, rather than engineering challenges requiring innovation. The Pennsylvania Railroad was operating with design philosophy that Baldwin's consultants had dismissed as reckless over-engineering. Boiler pressure reached 205 pounds per square inch, when standard practice limited passenger locomotives to 180. Cylinder diameter of 23.5 inches, delivering power that no Atlantic-type frame was built to withstand. Sustained speeds exceeding 90 miles per hour on schedules that European and American engineers publicly stated would destroy any locomotive within its first year of service. Alfred Gibbs stood in Baldwin's Philadelphia engineering office on a gray November morning in 1908, holding specifications from PRR's motive power department that would define his career. The document was straightforward and seemingly impossible. Design Atlantic-type locomotive capable of sustained 90 mph operation hauling 6-car bouts. Passengers must maintain schedule reliability equivalent to existing 60 mph service locomotives. Gibbs read the specifications 3 times before walking to the testing department where Baldwin had built its reputation on conservative engineering that prevented field failures. The problem wasn't revolutionary. Railroads had been chasing higher speeds for decades, but PRR's approach rejected every safety margin that prevented locomotives from self-destructing under operational stress. The specifications that mattered seemed designed to guarantee mechanical failure. Boiler pressure of 205 pounds per square inch pushing against cylinder heads that would experience forces exceeding 87,000 pounds during each power stroke. Driving wheels 80 inches in diameter created rotational speeds that turned every frame stress calculation into predictions of catastrophic structural failure. Combined tractive effort reaching 31,275 pounds delivered through mechanisms that conventional locomotives protected through deliberate power limitations. Baldwin's senior engineering staff had gathered in December 1908 to evaluate PRR's E6s proposal, and their reaction was predictably cautious. High boiler pressure means increased maintenance and shortened service life, argued Robert Henderson from Baldwin's boiler design department. Railroads want locomotives that run for decades, not experimental machines that might achieve impressive speeds before destroying themselves. But Gibbs had convinced PRR's mechanical department that the E6's concept could work by abandoning conventional assumptions about structural limitations. The key wasn't building heavier frames or accepting reduced performance. It was understanding that previous Atlantic types had failed not from insufficient strength, but from poor distribution of the massive forces high-speed operation generated. The frame design violated every principle of conservative locomotive construction. Instead of the standard 5-inch depth that Baldwin recommended for Atlantic types, Gibbs specified 7-inch frame rails with reinforcing gussets at every point where driving boxes and cylinder castings concentrated stress. Each frame rail would be forged from single steel billets rather than built up from multiple components, eliminating the welded joints where conventional locomotives cracked under sustained high-speed operation. Cylinder design demanded even more radical approaches. Standard practice placed cylinders outside the frame rails to simplify maintenance access. But this created torsional stresses that twisted frames during the power strokes at high speed. Gibbs positioned cylinders between frame rails with massive cast steel saddles that distributed power delivery forces directly into the locomotive's structural backbone, rather than applying them as twisting moments that conventional frames couldn't withstand. European observers learned of the E6s project through technical publications and responded with analysis that questioned PRR's engineering judgment. Heinrich Müller, chief mechanical engineer for German state railways, published detailed calculations in Locomotive Engineering Quarterly, demonstrating why Gibbs's design would fail. Sustained operation above 80 miles per hour creates harmonic vibrations that amplify with speed, Müller wrote. No Atlantic-type frame can withstand these forces. The PRR locomotive will experience catastrophic failure within 100 miles of service. Even PRR's board questioned the financial wisdom of pursuing unproven high-speed designs when conservative locomotives provided reliable service at speeds the traveling public considered adequate. Board member Charles Roberts had invested specifically because of PRR's reputation for operational reliability rather than engineering experimentation. The March morning in Altoona brought challenges that would test every assumption Gibbs had made about high-speed locomotive design. The first E6s frame arrived from Baldwin's Forge facility, and dimensional inspection revealed problems that conventional manufacturing practices had never encountered. The 7-inch frame rails showed microscopic variations in steel density that could propagate into stress cracks under the sustained forces of 90-mile-per-hour operation. Master mechanic Thomas Whitley had supervised locomotive construction for PRR since 1891, and his experience with Atlantic types made him skeptical of Gibbs's unconventional approach. We're asking 1908 metallurgy to handle forces that no previous passenger locomotive ever experienced, Whitley told Gibbs during inspection of the frame components. These frames need to flex slightly under load to absorb road shock, but stay perfectly aligned to prevent binding in the valve gear and driving boxes. The solution required manufacturing precision that exceeded normal locomotive construction standards. Every frame rail underwent stress testing that measured flexibility under simulated operational loads before installation. Quality control rejected components that showed variations exceeding 0.003 of an inch from specifications, tolerances typically reserved for watch mechanisms rather than 80-ton locomotives. Boiler construction presented even greater challenges. The 205 pounds per square inch working pressure required steel plate thickness and riveting techniques that pushed 1908 fabrication capabilities beyond established safety factors. Standard boiler practice used quarter-inch steel plates with lap-jointed seams that provided adequate strength for conventional pressure levels. The E6s demanded a 3/8-inch plate with butt-jointed seams and double rows of rivets at every stress point. Whitley's team discovered during initial pressure testing that the firebox crown sheet, the top, surfaced directly above the flames, experienced temperature differentials that caused localized stress concentrations. Conventional locomotives avoided this problem by limiting boiler pressure and accepting reduced performance. Gibbs developed an innovative crown sheet design using arch tubes that improved water circulation and eliminated hot spots that would have caused metal fatigue. The valve gear system required complete redesign to handle the combination of high speed and high power that no existing mechanism was built to deliver. Walschaerts valve gear was standard on American locomotives, but conventional designs used components dimensioned for moderate speed service. At 90 miles per hour, piston speeds reached 2,100 feet per minute, velocities that generated forces capable of shattering standard valve rods and eccentric straps. Gibbs specified chrome-nickel steel alloys for every valve gear component, materials typically reserved for armor plate and artillery rather than railroad equipment. Each connecting rod underwent individual balancing to ensure that reciprocating masses remained in perfect harmony at speeds where tiny imbalances would amplify into destructive vibrations. By September 1909, the first E6s stood complete in Altoona's erecting hall. Locomotive number 460 represented 3 years of engineering development and manufacturing innovation that challenged every assumption about what steam power could reliably deliver. October 3, 1909. The telegraph from PRR's Fort Wayne division arrived at Altoona headquarters carrying news that vindicated every critic who had predicted the E6s would self-destruct. Number 460 experienced severe driving box overheating during high-speed trials. Bearing temperatures exceeded 400 degrees Fahrenheit. Recommend immediate service withdrawal pending redesign. Gibbs read the message and understood that Baldwin's consulting engineers had been partially correct about one critical weakness. The locomotive could generate the power and withstand the frame stresses, but the driving boxes, the bearing assemblies that supported 80-inch driving wheels spinning at unprecedented speeds, were failing exactly as conservative engineers had predicted. The failure occurred during what should have been a routine acceptance test. Engineer Michael Sullivan had pushed the number 460 to 92 miles per hour on a straight track west of Fort Wayne, maintaining that speed for 14 consecutive miles with a 6-car passenger consist. Everything performed flawlessly until Sullivan noticed a smoke rising from the right rear driving box. Temperature gauges showed bearing metal approaching the melting point where catastrophic seizure would destroy the entire wheel assembly. Sullivan managed to bring the locomotive to a controlled stop using minimal braking to avoid shocking the overheated components, but the incident provided ammunition for every engineer who had warned that high-speed Atlantic operation was mechanically suicidal. Heinrich Müller's analysis, published just weeks after the Fort Wayne incident, dissected the bearing failure with precision that seemed prophetic. Driving wheel speeds exceeding 500 revolutions per minute generate frictional heat that conventional lubrication systems cannot manage, Müller wrote in American Railroad Journal. The Pennsylvania Railroad locomotive demonstrates why established engineering limits exist, not to constrain innovation, but to prevent predictable mechanical failures that endanger both equipment and passengers. Baldwin's Robert Henderson arrived at Altoona before the damaged locomotive returned from Fort Wayne, carrying calculations that challenged Gibbs's entire design philosophy. The bearing failure isn't an isolated incident, Henderson argued during an emergency engineering conference. At 90 miles per hour, your driving boxes are experiencing bearing loads that exceed design specifications by 40%. No amount of redesign will overcome fundamental physics. But Gibbs had discovered something crucial during his examination of the failed bearing assembly. The driving box itself remained structurally sound despite temperatures that should have caused warping and distortion. The actual failure occurred in the lubrication delivery system, specifically the mechanical lubricators that couldn't supply oil fast enough to maintain protective films between bearing surfaces and axle journals at sustained high speeds. The solution required abandoning conventional gravity feed lubrication in favor of forced feed systems that actively pumped oil into bearing surfaces under pressure. Gibbs developed a system using small displacement pumps driven directly from the locomotive's crosshead motion, ensuring that lubrication delivery rates increased proportionally with engine speed. Higher speeds meant faster pumping cycles that maintained adequate oil flow regardless of operational demands. Winter testing in Pennsylvania revealed that the lubrication redesign solved the bearing temperature problems but exposed another challenge that European critics had predicted. Sustained high-speed operation generated harmonic vibrations in the boiler that caused stay bolt loosening. The threaded rods that held firebox plates together under pressure threatened to work free from vibration cycles that no conventional locomotive ever experienced. May 15, 1910. The Pennsylvania Railroad's Chicago-New York route represented the ultimate test for any high-speed locomotive. The 912-mile journey demanded sustained speeds exceeding 85 miles per hour on segments where conventional locomotives required helper engines or speed restrictions. William Cassatt had committed 6 E6s locomotives to this brutally demanding service despite engineering reports warning that sustained high-speed operation would destroy the machines within 6 months. Engineer Patrick O'Brien prepared number 462 for its first revenue run with systematic attention to details that separated reliable operation from catastrophic failure. He verified forced feed lubricator pressure on all driving boxes, 45 pounds per square inch, maintained through the crosshead-driven pumps that Gibbs had developed after the Fort Wayne bearing crisis. Boiler pressure showed 203 pounds per square inch, just below maximum working pressure that conventional wisdom said would cause stay bolt failures. The moment of truth came at 6:47 a.m. when O'Brien released brakes and opened the throttle for departure from Chicago's Union Station. Number 462's 80-inch drivers began their rotation with 6 Pullman cars trailing, 1,200 passengers whose safety depended on a locomotive that Baldwin's senior engineers had predicted would shake itself apart under exactly these operating conditions. The first critical test came 90 miles east of Chicago, where the route profile allowed sustained maximum speed operation. O'Brien gradually advanced the throttle while monitoring cylinder pressure and frame vibration levels that Gibbs had warned required constant attention during high-speed running. At 88 miles per hour, number 462 settled into smooth operation that defied every prediction about harmonic destruction. The forced feed lubrication systems maintained bearing temperatures below 180 degrees, despite driving wheel rotational speeds that generated forces, Henderson's calculations said, would cause immediate seizure. Frame rails absorbed the massive power delivery stresses through Gibbs's reinforced design without the cracking that Mueller had guaranteed would occur within weeks of service entry. But O'Brien encountered an unexpected challenge that revealed both the E6s's capabilities and its demanding operational requirements. A freight train running late on the eastbound main forced number 462 to reduce speed to 45 miles per hour for 7 miles, exactly the kind of speed variation that critics warned would cause thermal stress failures in the high-pressure boiler. The rapid throttle reduction that conventional locomotives handled routinely created pressure surges in number 462's 205-pound boiler that threatened to lift safety valves and waste steam. O'Brien managed the transition by carefully coordinating throttle, blower, and firing rate, techniques that required skill levels beyond what standard passenger locomotives demanded from their engineers. The remainder of the Chicago-New York run demonstrated capabilities that transformed PRR's passenger service economics. Number 462 maintained schedule times that were 73 minutes faster than conventional locomotives managing the same route. No bearing failures, no frame cracks, no boiler problems beyond the operational challenges that proper training could manage. 912 miles covered at average speeds exceeding 68 miles per hour with maximum speeds touching 94 miles per hour on favorable segments. December 8, 1911. The winter storm that hit western Pennsylvania created conditions that should have validated every warning about the E6s's supposed structural weaknesses. Engineer James Mitchell faced a choice that would either prove the locomotive's durability or confirm critics' predictions about catastrophic failure under extreme stress. The New York-Chicago Limited was running 40 minutes behind schedule due to snow accumulation that had forced speed restrictions across Ohio. PRR's operating department demanded that Mitchell make up lost time using number 465's superior speed capabilities. But attempting high-speed operation in blizzard conditions with rail temperatures at 15 degrees Fahrenheit violated every safety protocol designed to prevent thermal stress failures. Mitchell pushed number 45 to 9 miles per hour through driving snow that coated every external surface with ice. The combination of sustained maximum power output and extreme cold created thermal gradients across the boiler that conventional engineering wisdom said would cause catastrophic stay-bolt failures, metal expanding from internal pressure while contracting from external cold, stress conditions that no locomotive design was meant to withstand. The crisis came 47 miles west of Altoona when Mitchell heard the distinctive sound that every engineer dreaded, the sharp metallic crack of overstressed components reaching failure limits. European observers would later cite this incident as proof that high-pressure, high-speed operation inevitably led to structural destruction. But what happened next would become legendary in PRR locomotive history. Mitchell immediately reduced throttle and prepared for emergency procedures, expecting the boiler failure that Mueller's calculations had guaranteed under exactly these conditions. Instead, number 45 continued running smoothly despite the alarming sound. Inspection at Altoona revealed the source. A side rod retaining bolt had sheared from a combination of cold brittleness and vibration stress, but Gibbs' redundant fastening design had prevented the rod from separating completely. The locomotive had absorbed a component failure that should have caused wheel lockup and derailment at 89 miles per hour in blizzard conditions. The redundant engineering that critics had mocked as unnecessary overbuilding had prevented disaster while allowing continued operation to the next service point. More importantly, the boiler showed no signs of the stay bolt loosening or thermal stress cracking that conventional wisdom predicted was inevitable. Thomas Whitley's detailed inspection of number 4i5 after the winter incident revealed why the E6s was surviving conditions that destroyed conventional high-speed locomotives. The 7-inch frame rails were absorbing and distributing stresses in ways that prevented the concentrated loading that caused cracking in standard designs. The reinforced boiler construction with its innovative firebox crown sheet design was handling thermal cycling that would have caused failures in locomotives built to conventional specifications. The Pennsylvania Railroad's operational data from 1911 told a story that engineering theory said was impossible. 6 E6s locomotives had accumulated 1 to 4 million miles of high-speed service with 0 catastrophic failures. Average speeds on premium passenger runs exceeded those of any other American railroad. Maintenance requirements were actually lower than comparable conventional locomotives because components weren't operating at their stress limits, despite higher performance levels. March 1914. Heinrich Müller's final report transmitted to German state railways acknowledged what European locomotive engineering had refused to consider possible. His conclusions appeared in the International Railway Engineering Journal with the careful precision of a man whose fundamental assumptions about steam locomotive limitations had proven incorrect. The Pennsylvania Railroad E6s Atlantic demonstrates that previous limitations attributed to mechanical impossibility were actually limitations of conventional design thinking, Müller wrote. Sustained speeds exceeding 90 miles per hour with heavy passenger consists can be achieved reliably through systematic engineering that addresses stress distribution rather than accepting arbitrary performance boundaries. The admission marked a turning point in global locomotive design philosophy. By 1915, orders for E6s pattern locomotives overwhelmed PRR's Altoona facilities, while Baldwin Locomotive Works developed competing designs based on Gibbs's frame reinforcement and forced lubrication principles. The concept that engineers had predicted would self-destruct had instead established new standards for what steam power could reliably deliver. William Cassatt reviewed operational data that vindicated every controversial decision made during E6 development. 83 E6 locomotives were now operating across PRR's system with average service lives exceeding projections for conventional designs. The frames that Henderson swore would crack within months were showing minimal wear after years of sustained high-speed operation. Boilers that Müller calculated would fail from stay-bolt loosening were maintaining pressure integrity through maintenance cycles that conventional wisdom said was impossible. The financial impact exceeded even optimistic projections. PRR's passenger service revenue increased 34% on routes where E6 locomotives reduced schedule times while maintaining reliability standards that passengers associated with slower conventional service. Competitive railroads faced the choice of developing their own high-speed capabilities or accepting permanent disadvantage in the premium passenger market. But the true legacy extended beyond commercial success or technical vindication. The E6s had proven that established engineering limitations often represented failure of imagination rather than fundamental physical constraints. The locomotive that should have torn itself apart had instead demonstrated that systematic analysis of stress distribution and force management could expand performance boundaries that tradition accepted as immutable. Alfred Gibbs understood that PRR had accomplished something beyond building faster locomotives. American mechanical engineering had challenged conventional wisdom about steam power limitations and won through methodical innovation rather than reckless experimentation. The E6s represented proof that rigorous analysis could identify why previous designs failed and develop solutions that transformed supposed impossibilities into reliable operational reality. By 1920, some E6s locomotives had exceeded 2 million miles of service, while maintaining the structural integrity that critics had predicted would last mere months. Number 460, the first locomotive that nearly failed during Fort Wayne testing, was still operating premium passenger runs at speeds that contemporary engineers had declared mechanically suicidal. The machine built to self-destruct had instead become unbreakable through engineering that understood forces rather than feared them.